So in this video we're going to find the slope and concavity of parametrically defined curve at a specified point. So in this example it says find the slope and the concavity of the plane curve described by x equals the square root of t and y equals 3 times t squared plus 2 for the interval t greater than or equal to 0. And we need t to be greater than or equal to 0 because that's the domain of the square root function right here. And we're asked to find the slope and concavity at a given point, at the point 254. So there's going to be a value of t that gets plugged into the parametrically defined curve that generates this point. So what we need to do is use one of the two parametric equations to determine the value of t. And in this case it looks like this will be the simpler one to use. So when x is 2, we have the square root of something generates 2. So squaring both sides, we see that time is 4, or t is 4. The parameter is equal to 4 for the point 254. If we wanted to verify things, we plug the 4 into y. We get 4 squared is 16 plus 2 is 18. 18 times 3 is going to be 30 plus 24 is 54. So indeed t equal to 4 generates both the x and the y coordinate for this point. Once we know what time is, we're being asked here to find the slope, which means we need to know dy dx. So dy, let's do it up a little higher. We need to know dy dx. And from the first video that we did, we know that dy dx is going to equal d dt of y of t over d dt of x of t. So we need to find the t d dt of the square root of, d dt of 3 times, I keep wanting to say the time derivative, but t in this case isn't necessarily time. We don't have any context. And the denominator is going to be d dt of the square root of t, which is the same as t to the half power. So the derivative of the numerator with respect to t is going to be 6t. And the derivative of the denominator with respect to t is going to be 1 over 2 times t to the 1/2. And if you needed to verify that, you could think about how would you take the derivative of t to the 1/2. Well, you'd get 1/2 t, and then you go 1/2 minus 1. We reduce the exponent by 1 would give us negative 1/2. And to make that exponent positive, we can move it down into the denominator, the variable t down into the denominator position. And then all we need to remember here is that when we are dividing by a ratio, it's the same as multiplying by the reciprocal. So this is the same as 6t times 2t to the 1/2, which is going to equal 12t to the 3/2 because we add the exponents. This is t to the 1 times t to the 1/2 equals t to the 3/2, except you need the t. So this is the derivative. This describes the slope of the lines. So when t equals 4, dy dx, because t equal to 4 corresponds to the point at which we want to know the slope of the line. So dy dx is going to equal 12 times 4. Replace t with 4, so 4 to the 3/2 is going to equal 12 times 4 to the 3/2. The 2 in the denominator says take the square root of 4, which is 2, and the 3 in the numerator says cube that result. So the square root of 4 is 2, 2 cubed is 8, so it's 12 times 8, which equals 80 plus 16, which equals 96. So at the point 2,54, the slope of the line is 96. And then we need to identify the concavity of the curve at this point. So what we need to remember for concavity, if we're concave up, the slopes of the tangent lines go from positive to 0, and they they go from negative, it's a negative tangent line, not doing so well here, negative tangent line transitions to 0, then the tangent lines as you sweep through the curve become positive. So to go from negative to 0 to positive, the second derivative needs to be positive, because the second derivative is the rate of change of the tangent lines, or the first derivative. So the rate of change of the tangent lines needs to be positive to get the tangent line slopes to go from negative to 0 to positive. Similarly, if we were concave down, the tangent lines would start off with positive slope. It would go to 0, and then we would swing through to a negative slope. So the second derivative, which is the rate of change of the first derivative, would need to be negative if the graph is concave down, in order to change the sign from positive to negative on the tangent lines. So to test concavity, what we did in Calc 1 was we used the second derivative test. Second derivative test. And if we had a positive second derivative, we knew we were concave up, and a negative second derivative meant we were concave down. So we know our first derivative, so we're going to need to take the second derivative. We need d2y over dx2, which is going to be just it's going to be defined to be d dt of dy dx. And this is from video 1, d dt of dy dx over d dt of x of t. So this is going to equal, we grab our derivative from our previous result. Here's dy dx. dy dx equals 12t to the 3 halves. So we need to take d dt of 12 times t to the 3 halves divided by d dt of our square root of t from up here. So t to the half. So this derivative is going to be 3 halves will come down. So we'll get 3 halves times 12 is 6 times 3 is 18. T, reduce the exponent by 1, so 3 halves minus 1 is going to equal a half. And then we already saw the derivative of t to the 1 half from our previous result was going to be 1 over t to the 1 half power equals, and again we're dividing by a ratio, so we get to multiply times the reciprocal, and t to the 1 half times t to the 1 half is going to equal t to the first power, so we get 18t. And then we use the second derivative test. We say, what's the sign of the second derivative when t equals 4? So when t is equal to 4, d2y of dx2 is going to be equal to just 18 times t, but t gets replaced with 4. And I don't even need to evaluate this result. What I notice here is I have a positive times a positive, which is going to be a positive number. So this means that this result is going to be greater than 0. And then we can make our conclusion, because the second derivative, d2y over dx2, is positive or greater than 0, the curve is concave up at that point 2, 54.